Hello everyone. In this video, we're going to be talking about the budget constraint and the utility maximizing consumption bundle. When we're doing this, we're returning to an idea that we've introduced previously called the feasible frontier. So the feasible frontier tells us the ideas or the set of things that is feasible in terms of what constrains the person in their utility maximization. The budget constraint is going to be doing the same thing. The budget constraint is just a special case of a kind of feasible frontier. Okay, so let's think about this. I'll get into the assumptions in a little while, but for the moment, let's just think about Harriet's total amount of money. So Harriet is our agent, she's the person who's acting, and Harriet has a total amount of money available to spend, and that amount of money is M. Now her budget set states what bundles, X and Y, are feasible for her to consume given her budget and the market prices of the goods. So what we want to think about here is that the amount of money that she has, M, that's going to be greater than or equal to the price that she spends on good X multiplied by the quantity that she spends on that good, and the price of good Y multiplied by the quantity of Y that she consumes. So the basic idea here is that you have the prices of the two goods you consume, the amount of them that you consume, and then your amount of money. You can't spend more on the goods that you want to buy than the amount of money that you have access to. Now, this is where the assumptions come in. We're assuming that you've got no gifts, that you can't steal stuff from anyone, and that there's no kind of consumption as a matter of like rights of being a citizen. So you're not just getting some good free of charge. So when we think about this, if you think about something, say, like radio, right? If you just have a radio and it's being provided as a public good, then that's something you're able to get free of charge. The price of it is zero. Then there are other assumptions that we can think about here. There is no altruism. There are no concerns about the environmental sustainability. You're going to consume the most that your budget allows you to. So when you're maximizing your utility, you're not concerned about other things other than your consumption, right? And just paying the prices for the goods that you can consume. Okay, so with those in mind, we're going to now consider Harriet's consumption of coffee and data on some axes. We're going to think about what's feasible for her to do on axes to do with coffee and data. Okay, so let's look at a figure like this. Here we have on the x-axis kilograms of coffee, and we have on the y-axis gigabytes of data. Now, the budget constraint, we had the budget being m equal to pyy plus pxx. If we rearrange that and make y the kind of the function of x, right, then m is a parameter here which says how much money she has, and then we say that y is equal to her amount of money divided by the price of y. That's this first term here, and then we subtract from that the price ratio px divided by py multiplied by x. Now, that is our budget constraint equation, just slightly rearranged. So what does that mean? It means that when Harriet consumes no x, so if this x term were equal to 0, what would she then have? She would only consume m over py of y. That would be this point over here at the intercept with the y-axis. Similarly, if she only consumed x, then she would have m over px of x that she would consume. And then in terms of points in between, we then have different points along the budget constraint that she could pick. She can also pick points in the feasible set that are within her budget, but if she did so, she wouldn't be exhausting her budget. Okay, so we had the budget constraint m equals greater than or equal to pxx plus pyy, and this budget constraint equation can be rearranged, as I just said, to express it as y equals m over py minus px over py times y. What have we done there? We've just made y the subject of the equation, and we've rearranged the terms. Okay, now the budget set is shaded in green, and the budget constraint is the dark green line. So this dark green line is the budget constraint. Now, any of the points in the light green space, those are feasible, but if you choose those points, you are not exhausting your budget. If you're on the budget constraint, the dark green line, then you are using up all of your budget to spend on the goods X and Y. Okay, so when we think about this, the negative of the slope of the budget constraint is the relative price, and it measures the opportunity cost of obtaining X in terms of the amount of good Y that must be given up, because funds are limited. So what are we thinking here? Basically, this price ratio, px over py, That's telling us the opportunity cost of getting more X in terms of Y. So when I think about the price of good X and the price of good Y, the price of coffee and the price of data, when I take the relative price of those two goods, that's telling me about the opportunity cost of getting more kilograms of coffee in terms of the number of gigabytes of data I have to give up. Okay, so I've got to give up some data in order to get more coffee, or going the opposite direction, I have to give up some coffee in order to get more data. Those are the opportunity costs that I'm confronting here when I'm trying to consider these two goods. Now, the negative of the slope of the budget constraint, that also tells us the terms on which a reduced amount of good Y can be kind of transformed into the additional units of good X while satisfying the budget constraint equation. So what is that about? Mathematically, the negative of the slope of the budget constraint equals the price ratio px over py, and that's the marginal rate of transformation. Remember, the marginal rate of transformation is always defined as the negative of the slope of the feasible frontier. So here, when we have a budget constraint, the budget constraint is a special case of a feasible frontier, and so the negative of the slope of the budget constraint is equal to your marginal rate of transformation. It is the thing that constrains the actor when she's trying to maximize her utility, and it is that which tells us the opportunity cost for her in terms of what she would like to achieve. Now, in order for us to think through her utility maximization, we can't do that without indifference curves. So here we have a set of 3 indifference curves for Harriet, U1, U2, and U3, in terms of the two goods, kilograms of coffee and gigabytes of data. So, a reminder, Harriet's marginal rate of substitution is her willingness to pay to get more of good X in terms of how much good Y she would be willing to give up to get one more unit of good X. Okay, so what this mathematically is the ratio of the marginal utilities. It's the marginal utility of X divided by the marginal utility of Y, and that's the negative of the slope of her indifference curve. Now what we want to remind ourselves of is what is the condition for which that tells us when Harriet will maximize her utility. That condition is when the marginal rate of substitution, her willingness to pay in goods Y for good X, is equal to her marginal rate of transformation, her opportunity cost in terms of what she's constrained to do for sacrificing good Y to get more good X. Now, what do we need for that? We need MRS equals MRT, which means we need both our indifference curves and our budget constraint. So let's see exactly that right now. Just as a reminder, there's the condition, MRS equals MRT. And so to get to her highest indifference curve, given her budget, she must choose the point where her budget constraint is tangent to her indifference curve. That occurs here at point B. So at point B, what do we see? We see that MRS equals MRT. We see that the ratio of the marginal utilities for the two goods, UX over UY, equals the ratio of the prices, PX over PY. So what she's willing to pay in terms of how much she is willing to pay of Y to get an additional unit of X, that's equal to what she's constrained to sacrifice in terms of her Y for X, the opportunity cost. So that's what the condition is telling us here. We've got the tangency of the budget constraint to the indifference curve, that highest indifference curve that she can achieve. And when we think about this, what can we remind ourselves of? There are two other points here, A and B. We looked at similar points previously when we looked at feasible frontiers. Now at A, what's the problem? At A, what can we see? The slope of her budget of her indifference curve is steeper than the slope of her budget. So if we just look at those two lines there, what does that mean? It means that her marginal rate of substitution is greater than her marginal rate of transformation. Because of that, she's willing to pay more Y to get an additional unit of X. So what should she do then? She should give up some Y in order to get more X. Okay, and that's what she should do in order to move towards point B and increase the utility that she receives. At point C, it's the opposite. The slope of the indifference curve is flatter than the slope of the feasible frontier, or the budget constraint. And so because of that, her marginal rate of substitution, or her willingness to pay of Y for X, is lower than the opportunity costs. Therefore, what should she do? She should basically give up some X in order to get more Y. She wants to go up her Y-axis and get more units of Y and give up some of the X that she has. She's got too much X. So if she were to do that, she would then reduce the amount of X that she consumes, get more Y, and in so doing, move towards the point where she has MRS equal to MRT, which is where she maximizes her utility.